Hi, welcome back. This will be the last session for the unsupervised learning. So in this session, I'd like to provide some high-level view of the Gaussian mixture model. And after that, we try to understand the basic idea about the expectation maximization algorithm in the Gaussian mixture model. So suppose that the data set below will be generated from the certain distributions, probability distributions. Then, how we can find out that distribution? There is some kind of question I'd like to ask you. All right, so assume that probability distribution is a Gaussian distribution. So this is the kind of the PDF for the Gaussian distributions. And the question of how we're going to find out the distribution based by using this data is equal to how we're going to find out the parameters that characterizing the Gaussian distribution, which is the mu and sigma. So basically, finding the probability distribution is same as finding the parameters of the distributions, right? Mu and sigma. So the question is, how we're going to find out the good parameter, right? To identify the probability distributions. So in order to do so, we need some measure, right, to find out the value of the parameters, the mu and sigma. So let's take a look at the one-dimensional data cases with the n observed data, right? And we define the likelihood of the parameter mu and sigma square. That is equal to, for example, this one. So this is kind of the likelihood of the getting this xi observation from the distribution having the parameter mu and sigma squares. So likelihood function is the function of the parameter mu and sigma squares, and that explain the probability or likelihood of getting n observed data. That is nothing but of this, right? And that is called the likelihood functions. And basically, given that mu and sigma is now known, we want to find them maximizing this likelihood function. And likelihood function is expressed as a product of this probability. So instead of using the likelihood function directly, we first take the log transformation. It's like this, because we can have the expression of the summation of the terms, right, after we taking the log transformations. And then still, as we know, the log function is the increasing function, right? It's to preserve the increasingness, right? So the increasing properties. So instead of using the the likelihood function directly, we use the log transformed function. Right. So once we take the log transformation on the likelihood function, right, to identify the maximum, the value maximizing this likelihood function, we take the partial derivative with respect to the parameter mu and the gamma, right? Gamma is the function of the sigma square. So what we get is mu is some kind of sample average of the xi's, and this is kind of sample the variance, right? So these are the parameters that maximizing the likelihood function. So you can get some kind of the closed form functions. So in case of the n-dimensional data, the maximum likelihood estimation with the data x can drive the Gaussian distribution G with these parameters, right? Mu and sigma can be calculated in this way by using this data, right? So we think that with this parameter that maximize the likelihood function, right? The question is, what if we have this types of data, right? By taking a look at this graph, probably you see that we can cluster into the two parts, right? But if we can explain this data coming from the single distribution, it is somehow difficult to say, right? So, how we can explain the data with more than one Gaussian distribution? It's like this, right? So, one Gaussian distribution for this part, and another Gaussian distribution for this part. So, we can think about some kind of mixture of the Gaussian distributions to represent the data. So in the Gaussian mixture model, we try to assume that data are generated by the mixture of the Gaussian distributions. So what's the meaning of the mixture of the Gaussian? Mixture of the Gaussian is the weighted sum of the different Gaussian distributions. So assume that the data are generated by the mixture of the Gaussian distribution. Okay? So the mixture of the Gaussian distribution is expressed by the linear combination of the Gaussian distribution. So we have the parameter for each Gaussian distribution, mu and sigma, right? And we also have the weight for each Gaussian distributions. So we have the one more parameter, right? I would say lambda is the parameters of the mixture of the Gaussians. So basically, we try to estimate the unknown parameters W, mu, and sigma, which is the parameter of the mixture of the Gaussian. And still, we can apply the same logic. So what I try to say is we try to define the likelihood function, right, for the mixture of the Gaussian. And then we can, by solving it, probably we can find out the maximum likelihood estimation on these parameters. But the problem is the likelihood function of the Gaussian mixture model is somehow complicated. So it is somehow difficult to estimate the parameters of the maximum likelihood. So that's why we use some kind of the iterative algorithm called expectation maximization algorithm, which will be explained in the next slide. So I don't want to explain the details of the expectation maximization algorithm because it is somehow difficult, and I don't think it's good to take a look at the details about it. So in this slide, I just briefly give you the underlying idea about how the expectation maximization algorithm works to estimate to find out the parameters for the mixture of the Gaussian, right? So what I try to in the expectation EM algorithm, so in the initialization stage, you just arbitrarily set the parameter, and then let's say that is the lambda 0, and you just keep iterating with the two sub-step. One is the expectation, and the second step is the maximization. In the expectation step, given this parameter lambda 0, right, you calculate the expected value of the log likelihood function with respect to the conditional distribution under certain parameter lambda, let's say lambda 0, in this case t is equal to 0 because this is the initial the iteration, and you have the expected value of the log likelihood function, right? And based on that information, you try to identify the parameter that maximizes the expected value. So you keep updating the parameters from lambda t to lambda t plus 1, right? And you keep doing this until the variation of parameter is sufficiently small. In other words, the parameter converges to the certain value. So let's take a look at the examples. So suppose that we employ two Gaussian distributions, right? And let's say we initialize the parameter with lambda 0. So given that, by using the parameter lambda 0, so you can have the you can calculate the likely the value, right? So for each data point has some kind of conditional probability also show with the each Gaussian distribution, because we use a two Gaussian distribution and try to express the data is coming from the mixture of the two Gaussian distributions. So each data point has the condition. You can calculate the conditional probability, also show with each Gaussian distribution GI. That is called the membership probability, and I denote the by TI0. And conditional probability is based on the log likelihood function under the current parameter lambda 0. And let's say, with the lambda 0, you have some kind of the Gaussian distribution, the first Gaussian distribution and second Gaussian distribution. And you can calculate, I don't want to explain the details about how the formula of the TI look like, but basically it represents some kind of membership probability. So for example, this data point, let's think about this data point, and each TI, right, T1 is equal to 0.7, right, is more likely to coming from these distributions, right? And this is less likely, this data point is less likely coming from this distribution, right? Similarly, when it comes to this data point, it's a more higher probability to coming from this Gaussian distributions, right? So it has a higher value than this one, right? So you can calculate some kind of membership probability. And after that, with this information, you update to the value to find out the next parameters. So we can obtain some kind of expected value of log likelihood function with a conditional probability, right? So you can calculate the conditional probability, and then you can define some functions, and you try to maximize this expected value. You try to find out the parameter that maximizes the expected value of the log likelihood functions. And you try to find out lambda 1 that maximizes this expected value, right? Let's say that is a lambda 1. So you update. So let's say in the initial stage, Gaussian 1, the Gaussian 2 was located here, and then after the updating the parameter, and that is the Gaussian distribution 1 and new Gaussian distribution 2, right? And by using that information, you can also you can calculate this membership probability again. And you keep updating, right? And you keep updating the information, and by using that information, you can also define this expected value of the log likelihood function with the conditional probability, right? And then you can find out the parameters. So that is a kind of the iterative approach to find out the parameter that maximizes the likelihood function of the mixture of the Gaussian. So basically, in the EM algorithm for the Gaussian mixture model, parameters that maximize in the Q are indeed, for example, the W1 is the expectation of W0, and mu1 is the expectation of X with the membership probability TI, and the sigma, which is the parameter of 1 that maximizes this function, and that is the expectation of the covariance of the X with the membership probability of TI. So using this the membership probability, you can find out the parameters that maximize this expected value, right? So you don't actually need to solve this optimization model. You just simply calculate the next parameter based on that information, right? So once you know the parameter value x lambda 0, and you also know the membership probability, by combining it, you can calculate the parameter in the first iteration. And by using it, you also calculate the membership probability on the first iteration. By combining it, you can define the parameter at the second iteration, and so on. You can keep doing this until you the difference of the parameter is sufficiently small. That is the convergence, right? So you iterate in the previous step with a new obtained parameter lambda 1 until the variation of the parameter is sufficiently small. Right, so there are some issues. Issues in the Gaussian mixture model is, how many Gaussian distributions we need to consider as a mixture of the Gaussian distributions. Right? So we need to determine the number of Gaussian distributions. Right? In that case, is it 2 is appropriate, 3 is appropriate, 1 is appropriate? So we need to have some measure, right? So normally we use the BIC, which is the kind of the criteria for model selections. And by using the index, right, BIC index, so you can find out the lowest value of BIC. The corresponding value tells us the recommended number of the Gaussian distribution. And what is the application of the Gaussian mixture model? It can be used for clustering, and it can be used the novelty detection. Okay, so so far we quickly took a look at what the Gaussian mixture model is, and to find out the parameters, how the expectation maximization, the algorithm is applied to calculate the parameters, right? So that's it for that's it for today's session, right? And then we'll see on the next session. And then in the next session, I'd like to introduce the concept of dynamic programming in a Markovian process, and and so that we can better understand on the concept of the reinforcement learning. Right? So see you on the next session. Thank you.